And so it is now 3 p.m. Central European Time, 9 a.m. Eastern Standard Time, and I would like to kick off this seminar. I'm Gabor Fodor, currently serving as the chair for the Full Duplex Emerging Technology Initiative, and would like to welcome you all to this exciting seminar on reduced complexity interference cancellation algorithms of faster-than-Nyquist signaling by Assistant Professor Ebrahim Bedeer and Professor Halim Yanikomeroglu. Just a short note on the background from my point of view. As you might have heard or you might have seen in my email or in my invitation, the full duplex ETI is currently discussing a possible extension of the scope of the ETI, in the sense that this possible extension of our scope actually was also discussed at the recent meeting of the Emerging Technology Committee, chaired by Professor Wendy Heinzelman. And we agreed that we will explore areas that would highly benefit from the progression of interference cancellation techniques. And specifically, this extended scope may potentially include applications of self-interference cancellation techniques to other than full duplex communication. So that's why the extension is opportune. And now in this context, faster-than-Nyquist signaling may be a very important and interesting topic. And this seminar topic is thus very timely and highly relevant for the ETI. But without much further ado, I would just like to recall and especially welcome, and I'm so happy that Ebrahim and Halim accepted this invitation. As you might know, Ebrahim is an assistant professor at the University of Saskatchewan in Canada. His current research interests include applications of optimization techniques in signal processing and wireless communications, spectral efficient communication systems, and Internet of Things. And you may find more information about Ebrahim in the link that I sent out. Halim Yanikomeroglu is a professor at Carleton University, also in Canada, and his research interests cover many aspects of wireless communication systems and networks, and his collaborative research with industry has resulted in 37 granted patents. He's a fellow of the IEEE, the Engineering Institute of Canada, and the Canadian Academy of Engineering. And Halim is also a distinguished speaker for both the IEEE Communication Society and the IEEE Vehicular Technology Society. So very warm welcome, and we are all excited to and looking forward to your presentation, Ebrahim and Halim, and I give the floor to Ebrahim, please.
Yeah, let me share my screen. Did I share my screen successfully? Okay. Thank you, Dr. Fodor, for the introduction and for inviting us. I am happy and excited to present our recent research results on reduced complexity interference cancellation techniques for faster-than-Nyquist signaling. So this is a joint work with Professor Halim Yanikomeroglu from Carleton University. So my talk will be divided into two parts. The first part will be a short introduction. The first part will be a short introduction and a brief history about faster-than-Nyquist signaling, in case some of the audience are not familiar with the concept. And in the second part of the presentation, I will share some of our recent research. So we all know that there is a need and demand for higher throughput. And we need to find technical solutions to meet such demands. We can operate at higher frequency bands. We can use massive MIMO and all these technology. But today's talk is about a better use of the bandwidth and the design of more efficient modulation and coding. So we can view FTN as a candidate solution that can trade improvement in the spectral efficiency with higher signal processing complexity at the receiver or at the transmitter. So as we know, the Nyquist rate signaling, we can transmit 1/t pulses per second if we have a bandwidth over a bandwidth of 1/2 THz. And this is mainly to avoid the intersymbol interference, right? So the concept of the Nyquist rate signaling has been used for decades. And as an example, in the linear orthogonal pulse modulation, if the symbol durations will be capital T, pulses are T orthogonal, the optimal detection is a symbol by symbol basis because there is no interference, right? So the question is, so how can we transmit more bits per second per hertz? The classical solution here is to increase the modulation order. However, this will be at the expense of transmitting more power to support the increase in the constellation. The other option we are exploring is to relax the orthogonality constraint imposed by the Nyquist, imposed in the Nyquist rate, and eventually accept the intersymbol interference and find techniques or algorithms to remove this interference. So here we show faster than Nyquist signaling. As you can see on the figure on the right, the pulses are T orthogonal. T here is normalized to 1. However, the symbols are 10 faster in time every tau T, where tau is a parameter lower than 1. In this figure, 0.8. And it refers to the time acceleration parameter. So clearly, there will be symbol interference as expected. So the concept of violating the Nyquist rate limit is not new at all. The first published paper dates back to 1965, where researchers from Bell Labs showed that the bandwidth can be slightly smaller than the Nyquist limit without having catastrophic error rate results. However, the first to prove that the asymptotic error rate can be maintained even if the signaling rate exceeds the Nyquist limit by 25% was James Mazzo in his seminal paper in 1975. So what Mazzo did, he accelerated the transmission of sync pulses carrying binary modulation, of course, in uncoded transmission. And he observed the Euclidean distance between any two different signals employing FTN. And he observed that the minimum distance will be the same as the Nyquist signaling, as its counterpart orthogonal signaling, as long as the acceleration parameter is within a certain range. And this is 0.8 for the case he studied, which is the binary transmission of sync pulse. So this means that we can have 20%, 25% more bits in the same bandwidth operating at the same error. Mazzo results appear to contradict the Nyquist limit. However, this is due to confusing orthogonality threshold with the minimum distance threshold. So the Nyquist limit defines the bandwidth at which orthogonality can no longer exist, 1/2 THz. And the Mazzo limit, this is the bandwidth at which the minimum distance falls below its orthogonal value, 0.8/2T, which is clearly smaller than the Nyquist. However, since communication systems at that time were mainly limited by hardware and memory, also the theory of detection and equalization was not mature yet. So faster than Nyquist signaling as a concept didn't gain traction at that time. Over the years, the Mazzo limit extension, or the concept of Mazzo limit, has been extended to practical pulse shapes, for example, to root raised cosine pulses, where it was shown that for a 30%, as an example, a 30% excess bandwidth, the minimum distance will drop below the orthogonal value at acceleration parameter of 0.7, which means that we can have 42% more bits, same bit error rate, same signal to noise ratio and bandwidth. One of the important extension as well to the concept of Maso limit was in the frequency domain. So this is what is known as the two-dimensional Maso limit, or the multi-stream faster-than-Nyquist signaling. So here the concept also is quite simple. Packing subcarriers in the frequency domain beyond their orthogonality limit, of course up to a certain degree, will not result in deterioration of the bit error rate, and we maintain the same minimum distance. What is interesting here that we can have independent gains from the time domain acceleration and the frequency domain packing. And here it is important to point that the multi-stream FTN usually appears in the literature also as a time frequency packing. The concept of Maso limit has been extended to other domains as well, to MIMO transmission, to non-binary signaling, to even non-orthogonal pulses, to nonlinear modulation. But the common thing here that in all these extensions, the bandwidth at which the minimum distance drops below its orthogonal value will be always smaller than the Nyquist bandwidth. Here, let me emphasize that this doesn't mean we should limit our operation to only the Maso limit when it comes to use faster-than-Nyquist signaling in transmission. Actually, recent research results show that even accelerating the pulses much faster than the Nyquist limit, much faster than the Maso limit. So we are operating at values of tau that is significantly smaller than the Maso limit. And in the presence of coded system with the help of turbo equalization, we can have quite a significant spectral efficiency gain. So we shouldn't, this doesn't mean, as I mentioned, to limit our operation only to be within the Maso limit. Anyway, the intersymbol interference resulting from FTN theoretically of infinite length, especially if the small values of tau are used. And the problem as a detection problem can even be complex given that communication systems typically use high order modulation. So that's why there is a need to find detection techniques that can remove the intersymbol interference with reasonable detection complexity. So a typical communication system employing FTN will mainly have the changes in the modulator and the demodulator parts. So of course, here we are not discussing synchronization and the channel estimation, but building the modulator can be done in a number of ways. Perhaps the most widely used one is to use a pulse acceleration, where the pulses are T orthogonal, symbol intervals are shorter, tau T, or we can stretch the pulse in time by a factor of 1/tau and keep the symbol duration as T, or interestingly, FTN as a non-orthogonal transmission can be viewed as orthogonal transmission, but carrying much larger alphabet of real values instead of the M-array symbols. So at the demodulator, of course, we will have a filter matched to the pulse shape that is used at the transmitter. So depending on how the modulator was constructed, we may end up having colored noise samples or white noise samples. And there is an optional discrete time filter that performs a number of tasks, including whitening the noise if needed by the detector. The most important part here is what are the available options for detections, what are the trade-offs. So since the inter-symbol interference in the time domain or the inter-carrier interference in the frequency domain have a trellis structure, then trellis or tree search-based techniques can be used. However, as I mentioned, given the significant length of the ISI and the potential use of higher order constellation, they may be of impractical complexity. So that's why there are techniques to reduce the search over the trellis or somehow reduce the trellis and perform full search. And these techniques were shown to be give close to optimal performance, and they are quite promising at higher spectral efficiency gain when used with turbo equalization. Still, they are relatively complex, and the complexity varies exponentially in the inter-symbol interference length. Another promising type of detector for FTN is based on combinatorial optimization techniques. And our experience here showed that this type of optimization techniques may work quite well with high order modulation. We have explored a couple of these techniques, and we were able, for instance, to detect 16 QAM FTN signaling with reasonable detection complexity using semi-definite relaxation and Gaussian randomization. And recently, we were able to also design a detector for very high speed links that carry up to 16 bit per QAM symbol. And we are in the process of filing a patent for this detector. Anyway, so combinatorial optimization techniques in general are of low complexity when compared to the trellis or tree-based search techniques. The complexity order is polynomial in the inter-symbol interference length, and they are insensitive to the constellation size, and that's why they may have a room for application with high order modulation. However, they are only limited to a certain acceleration ranges, and we have seen they can give quite good performance for values of tau around 0.6, let's say. If the operation of the FTN will be within the meso limit to achieve small gains in the spectral efficiency, then other low complexity techniques, can be used for detection. For instance, frequency domain equalization is a promising candidate here. They use the FFT for the filtering. However, there is potentially spectral efficiency loss due to the use of the cyclic prefix. Precoding at the transmitter side is also quite promising in giving a good performance. However, also their operation is limited by acceleration ranges. So for those who are interested to learn more about this interesting signaling scheme, I highly encourage or suggest reading this paper published in the proceeding of the IEEE in 2013. So when it comes to the applications of FTN, it seems it is quite successful in fiber optic links. And here, the reason is mainly as deploying more fiber to meet the demands that we see every day is quite expensive and invisible solution. Also, the use of high order modulation in fiber may not be visible also due to the fiber nonlinearities. So here, FTN comes as a promising long-term solution to improve the spectral efficiency in fiber links. Also, it has been investigated for point-to-point links like microwave links, satellite digital TV broadcasting, underwater communications, and potentially with the help of symbol level precoding, it can be used also in cellular communication. So in the second part of the presentation, I will present a sample of our research results that we had while I was at Carleton in 2017. So FTN is a promising research direction, and it has a number of open research problems that need to be addressed. synchronization, channel estimation, reducing the PAPR for multi-stream or time frequency packing are important research points. And also finding low complexity technique in a number of scenarios, in a number of applications is also quite important. And this is the focus of our research in the past couple of years. Here we decided to present a very simple idea that can detect FTN on a symbol by symbol basis, comparable to the Nyquist signaling detection. So what we are trying to show here, that despite that the interference can be extensive, despite the complexity involved with the optimal detectors, but the interference has a specific trellis structure that is already known at the transmitter. And this structure can be exploited to find low complexity detection technique. So here, as you see, a received sample will contain, of course, the current symbol to be estimated, in addition to inter-symbol interference from previous symbols and the inter-symbol interference from upcoming symbols. Here we came up with these two conditions. We call them the perfect reconstruction conditions for Qpsk FTN signaling, assuming noise-free transmission. And simply, we can detect the current symbol from the current sample, regardless of the value of the upcoming symbols, regarding the length of the interference, if these two conditions holds. Just to help visualize the operating region of this scheme, so here we plot the spectral efficiency bound, of course, on the vertical axis, and on the horizontal plane, we can see the projection of the operation region where a symbol by symbol detector is possible for FTN. Of course, as expected, a simple technique like that may suffer from error propagations, and which is true. However, we can have layers of detection to improve the accuracy. So for example, here, this is what we call a symbol by symbol with go back K. The idea again is simple, based on the current symbol that is already have been initially estimated. We can go back and improve the detection accuracy of previous, let's say, K symbols, and in an iterative process, we can improve the performance. So despite the very simple detector that is proposed in this work, but it has been found to be quite interesting in the sense that of balancing the performance and the complexity when operating at higher values of the. So here we present the spectral efficiency results. So in the x-axis, this is the roll-off factor of the root raised cosine pulse. The red line represents Qpsk Nyquist signaling. The blue line represents Qpsk FTN signaling. And the comparison is fair in the sense that it is at the same bit error rate of 10⁻⁴, and also at the same signal to noise ratio. So as we can see, for a fair comparison, with a symbol by symbol detector with a complexity pretty much comparable to the conventional Nyquist signaling, we can have a 20% improvement in the spectral efficiency at practical values of the roll-off factor. Here we present also the spectral efficiency gains we have from one of our proposed technique that is based on relaxed combinatorial optimization techniques. Here we view the FTN signaling as a detection problem. We have discrete constellation constraints. So we managed to formulate that as a high degree polynomial, and then with a series of relaxations, formulations, we were able to put the detection problem in a form where we can use semi-definite relaxation and Gaussian randomization to detect 16 QAM FTN at a very reasonable detection complexity. So as we can see here, the blue line, this is the 16 QAM FTN. The red line, this is the 16 QAM Nyquist signaling, operating at the same error rate, signal to noise ratio, and we observe around 25% improvement in the spectral efficiency. If we can afford more detection complexity at the receiver, we can of course employ some tree search techniques. And again, a fair comparison at same bit rate and the signal to noise ratio show that our close to optimal technique here gives around 38% improvement in the spectral efficiency. So to conclude here, Nyquist limit, it's more of a guideline than a rule to design communication systems. The pulse orthogonality condition makes it easier to process these pulses. However, it will have loss in the spectral efficiency or the bandwidth. FTN signaling as a promising here in the sense that it can trade improving the spectral efficiency, save the bandwidth, versus increasing the processing complexity at the transmitter or the receiver or both. And it can be an alternative to high order modulation, or it can complement high order modulation. So that's my talk, and thank you so much for listening.
Thank you so much. I think we give you a hand first. Thank you for this. Very nice, insightful presentation. And I would like to ask the audience any questions or comments.
Gabor, sorry,
Yes.
I also have a short set of remarks. Should we do that first or after the audience?
Yes, Halim, please go ahead.
Okay. Ebrahim has already given a thorough presentation. I have just a set of high-level remarks. I find faster-than-Nyquist signaling truly fascinating for a number of reasons. Its history is fascinating, the theory is fascinating, and there are some hidden connections to many other fields which I do not understand very well, and that makes me even more fascinated. By the way, just a disclaimer, the person you are seeing right above my name is not me. It is, of course, Harry Nyquist, a Swedish engineer upon whose work we are trying to build today. As Ebrahim remarked, different sub-communities use different terminology, what we call as FTN. Signal processing, people sometimes call time frequency packing, by extension to frequency domain as well. And especially in the optical fiber community, the term generally used is super Nyquist, but they all refer to the same concept. Now I'm thinking, how often in our circles we start the discussion from a century ago, even before Shannon? That happens extremely rare, and this is one of those instances. Literally, the discussion goes to a century ago, and Nyquist's 1928 seminal paper was probably the most important foundational block for what we used to call Shannon theory, but I guess the community is recognizing more and more the contributions of others. Probably a better term is Hartley-Nyquist channel capacity theorem and formulation that came in late 1940s. Now, as Ebrahim mentioned, important milestone is the work in mid-1970s in Bell Labs by Mazzo, and I believe it was the Mazzo who coined this term FTN, but there were people who looked into this concept before Mazzo in Bell Labs, starting probably a decade ago, a decade before Mazzo. However, at the time, there was quite some skepticism among the Bell Labs people. It seems like that, and Mazur's work did not find due attention for quite a while. And we should remember that 1970s, the equalization theory is not there as developed today. The good work of Bob Lucky and many others are just unfolding. So interference is a terrible term. It is something to be avoided. So it seems that Mazur's ideas were not that welcome at the time. And very interestingly, there is a period of silence for almost 3 decades, kind of akin to Gallagher's PhD thesis reinvented as LDPC codes after several decades. We had to wait until 2000s when people started coming with some constructive designs. Mazur's formulation is pretty much non-constructive existence theorem. He shows from the minimum distance arguments that up to 1 over 0.8 or 2, I guess, which makes about 25% with Nyquist pulses without asymptotic performance loss, acceleration is possible. But then it was, I believe, the work of Liveris and Georgiades in 2003, which came up with actually building blocks. Here is a root raised cosine filter. Here is how we modulate it, how we demodulate. And then they argued that the concept has promise. And pretty much around the same time or right after, some faculty members, or I guess Rusek was a PhD student perhaps at the time, they started exploring this idea, and I call this era starting with 2005 for almost a decade, Rusek-Anderson era in faster-than-Nyquist signaling. They really bombarded the literature by looking at this phenomenon from very different angles. And also it is interesting, if you look at, I just checked Rusek's papers in Google Scholar in according to chronological order. His work before faster-than-Nyquist signaling was on correlative coding, partial response signaling. Some of you might be familiar with these concepts, which are more rudimentary forms of controlled interference. So again, a very subtle connection to partial response signaling of 1970s. And then another interesting development I think worth noting is EU FP7 project METIS at the pre-5G standardization identified this concept as a promising concept for 5G air interface, but I believe the concept was still rather premature and it didn't make it to 5G. I hope there might be some people in the audience who were part of this METIS 2020 influential platform, and they might perhaps allude after me why it wasn't pushed to 5G, this standardization. Now, I also did an interesting study. In IEEE Explore, I searched journal and conference papers with the key term faster-than-Nyquist. I only use that key term. So these are the papers faster-than-Nyquist either appear in the title or in the keywords of the papers. So 20 years ago, pretty much no activity. Interestingly, that one single paper at 2003 journal paper is the paper of Georgiades. And then this one single paper in 2005 is, I guess, in 4 as well, the 2005 paper, I believe the ISIT paper of Rusek and Anderson, which they extended time domain faster-than-Nyquist to frequency domain faster-than-Nyquist. And then in the next decade, some activity starts picking up. And I mentioned the main players in this era are still Rusek and Anderson and some other folks from Lund University. And 2007, these maybe 10 papers you are seeing, 8 of them are from the Lund University. Now, things changed in the last several years. Starting 2014, there is a sharp increase in the publications. First, we see a substantial increase in conference papers, and more recently in journal papers as well. And actually, last year, there were 28 journal papers at Explore, once again, either in the title or keywords Faster-Than-Nyquist appeared. Clearly, there is quite a bit of interest in the literature. Ibrahim mentioned that different communities have looked or are looking at this concept for a variety of reasons. In fiber optics, I believe the motivation is higher order modulation is difficult due to nonlinearities. Therefore, Faster-Than-Nyquist is a savior. In satellite communications, it's a power limited system. Therefore, increasing spectral efficiency by non-conventional ways is important. I believe the applications as product are still on the limited side, but I was told that some current microwave backhauling links do use Faster-Than-Nyquist signaling. And more recently, in search for the sweet spot of Faster-Than-Nyquist signaling, researchers identified interesting regimes. One of them is in cases where asymptotic studies are not possible. For instance, when you have a block length due to latency constraints, that is the URLLC scheme, Faster-Than-Nyquist signaling seems to be very promising. There is indeed a January 2021 paper, I believe, Communication Letters, building on this concept. And also through filter hopping, it has been articulated for physical layer security. In the audience, we have Damien from France. He brought some interesting work to my attention in this area. And then these very interesting connections, well, pretty much Faster-Than-Nyquist signaling is related to all the legacy things that we know, whether it is Shannon theory in signal processing and so on. But then the story does not end there. There is this phenomenon of super oscillation. And I will just read from the seminal paper of Ferrara and Ahim Kamp. I guess some of us are maybe not on mute. We might mute ourselves. This paper with the title, Super Oscillations Faster-Than-Nyquist Rates, which appeared in Transactions on Signal Processing. Ahim Kamp is one of the leading mathematicians in the quantum domain. And they bring to the attention of the community something very counterintuitive, and that is, well, let me read it here. It is commonly assumed that a signal band limited to μ/2 Hertz cannot oscillate at frequencies higher than μ Hertz. In fact, this may happen. And of course, there are conditions. Basically, the dynamic range of the time waveform should be extremely high. So what they are suggesting is that in some very special cases, which are difficult to observe in legacy systems, some magic might happen. And then this has implications apparently in quantum communications and some other fields. Really, the mathematics of this is beyond me. But once again, I find it very interesting. Sometimes this community make a reference as faster than Fourier, even going beyond Faster-Than-Nyquist. So here we go. We started with a century history, and now we are talking about 2 centuries. Now, let us wrap this up, this discussion. Has the time come for Faster-Than-Nyquist signaling? That is the big question. And I don't have obvious answer. Obviously, as a fan of this concept, I would very much hope to see this picking up. And two things make me hopeful in addition to what Ebrahim mentioned. One of them is, as time progressed, especially in the last 2 decades, as a community, we became more comfortable with non-orthogonal everything. So non-orthogonality is not a taboo anymore. So maybe it is time for a more courageous examination of this area. Also, as we all know, there is a potential enabler with which we are, as a kind of magic wand, we are trying to touch upon everything to see whether it will turn that thing into gold, and that is AI ML. Given that complexity is a concern in some of the applications, who knows, maybe AI ML might give us some clues for efficient signal processing. Just for fairness, not necessarily complexity is a big issue in some contexts, for instance, in the microwave links or at the base station, whether as an equalizer or pre-coding techniques, high complexity can be accommodated. The other big question is whether this particular ETI, Emerging Technology Initiative on full duplex, is the right platform to pursue the concept. And I believe Gabor and the officers of the ETI will make the decision. It goes without saying that self-interference, cancellation, or handling in full duplex in the form of uplink, downlink is very different than the controlled ISI cancellation or ICI in Faster-Than-Nyquist. Nevertheless, at the end of the day, all of these are different manifestations of self-interference. So to me, it sounds a logical extension of the scope of this ETI. And I am in touch with almost 10 universities. I call them my circle of FTN. With some of these universities, we co-authored papers, and with some of them, we recently got connected. I became aware, for instance, that at Peter the Great St. Petersburg Polytechnic University, some recent good work is going on. We had a video conference. And back in 2020 summer, we had the first Faster-Than-Nyquist virtual workshop. It was attended by, I believe, 40, 50 people. Very nice discussion. So, Gabor, I don't know how you would like to proceed, but rather than a direct Q&A, I think we have many experts on FTN in the audience. If they would like to make their comments, I would be interested to hear them. Thank you.
Thank you, Halim. We give you thank you. So, very, very interesting indeed, the historical look back. Yes, Halim, do you have in mind any particular expert you would like to invite, or I don't have otherwise a scheduling mechanism for?
Not necessarily. I guess the floor is open if anyone would like to make any comments. For instance, I know that Pascal and Damien from France have worked in this area substantially. If they would like to say or make remarks, or any other people. I see Risto, Taneli in the audience, so I guess all comments are welcome.
Very well. So the floor is open for questions and comments to Halim and Ebrahim.
Yes, perhaps I have some remark and question. Thank you very much, Ebrahim and Halim, for this very interesting presentation. To your opinion, as you mentioned, mostly application, do you think that actually there is still some receiver which are ready to be implemented operationally and which optimize in the best way the compromise between performance and complexity? Or do you think that there is some places for new research to be able to implement this receiver in faster-than-Nyquist links? What do you think of this?
Some constructs are in some ways easier than others. For instance, if we take the microwave backhauling links, It is point-to-point AWGN channel pretty much. There is no other channel impairments. There is no additional channel-induced ISI. So it wasn't, I believe, accidental that that community were among the first to look into this, and if I am correct, even to implement that. But if I go back to this historical development, after Mazos and Bell Lab pupils' work for the following 2-3 decades, this area was pretty much non-constructive study. Odd papers might be coming in transactions on information theory. A lemma is proven here, a lemma is proven there. So a more constructive history started less than 20 years ago. And even there, first uncoded and maybe low order modulation. And only recently, we are, I guess, as a community, are able to have a more profound construct. And still, many of the engineering issues perhaps have not been tackled properly yet. You know, if we are talking about ISI, for instance, synchronization, obviously I had a interesting email exchange with Damien on this issue. Certainly synchronization has to be looked into very carefully. As a matter of fact, I have a student who is starting looking into that. So if the question is this a block ready for implementation? It doesn't seem to be the case at the moment. And as a matter of fact, even theoretically, the bounds are not very well understood. I'm telling the obvious, but the Shannon bound is, of course, for infinite processing, infinite energy, you know, infinite block lengths. But in, say, IoT applications or low latency applications, if there is an energy budget, if there is latency budget, still with FTN, some theoretical guidance, I think, has to be there, which is not there at the moment as far as I see, or only there to certain cases. And that is in part make this a very interesting research paradigm as far as I am concerned, because although I have been working in this area for a couple of years now with Ebrahim and others, I still do not understand, position it precisely as a textbook entity with everything else that I know of. So that is telling me that still there is more to be understood. Nevertheless, I guess I started repeating myself. I think there might be a good potential there. You know, I'm just thinking, imagine an air interface, whether it is Wi-Fi, now Wi-Fi 7 discussion started, but Wi-Fi 8 or 6G plus. 6G is, I think, very close, perhaps, for FTN. We might have, and we have already adaptive modulation and coding tables, which are getting increasingly bigger and bigger. But imagine we have a multi-dimensional lookup table. Not only we change the modulation level and coding, but we also change the role of factors and even pulse shape rather than root raised cosine. There might be some other interesting pulse shapes. So this technology might have a role both in the low spectral efficiency regime and high spectral efficiency regime. We generally refer to increasing the spectral efficiency, but obviously another way of looking at it is at a given spectral efficiency, if FTN is resulting at a lower operational SNR in comparison to legacy techniques, here we go, there is a saving there. So I think there is quite some room to explore all those. Ebrahim, anything to continue on that? You are on mute, Ebrahim.
Oh, sorry. Yeah, so I was saying that perhaps no, I have nothing more to add. yeah, so I just stop here. Yeah.
Thank you for your opinion. Thank you.
Yes, Basma?
Yeah, thank you. So thank you both. It was a great presentation. I really enjoyed. So I want to just, before I start my very high level question, have a disclaimer that I never worked on Faster-Than-Nyquist, so I'm completely ignorant of that field, but I know the full duplex part. So my question is about this positioning and the link. So I can see through the presentation that we are both working toward the same objective, which is increasing the spectrum efficiency. I can see as a complementing, but are you thinking actually with the interference part, the struggle I have with, which is what makes full duplex special, is the interference is much, much higher than the signal. We're talking like 100 dB, 110 dB. Are you really thinking also about getting inspired from those tools? Did I miss that part?
Yeah, perhaps I can start to comment on that. Thank you, Professor Smeda, for the question. Yeah, so as you mentioned, the nature of the interference in full duplex and FTN, they are quite different. So the interference in FTN, it's also significant, but the significance here comes from the theoretically infinite intersymbol interference length. So comparing this to a dispersive channel, as if theoretically we have an infinite dispersive channel. So this is where the problem comes when it comes to FTN. But comparing this to the level of the interference that comes from full duplex, I think this is quite an interesting, discussion, and I think it needs, to be looked into carefully.
Yes, I will echo Ebrahim, and also, as I mentioned, the nature of self-interference is very different indeed, the dynamics. However, it is different types of self-interference, of course. So it is not an immediate extension. So it is a conceptual umbrella. I guess both of them can be put. One other difference, as in addition to Professor Smeda, what you mentioned, the orders of magnitude, of course, difference, which is not the case in Faster-Than-Nyquist signaling. Rather, it is a just explosion of ISI, but it is, of course, controlled. Another interesting observation there is that in full duplex, often the mechanisms are at the transmitter, at the node transmits and receive. In Faster-Than-Nyquist, in the first look, the ideas come into mind at the receiver side, but since this is a controlled interference, pre-coding can play a role. There are a high volume of papers, and depending on the uplink or transmitter receiver asymmetry, let us say, a lower end device communicating with a high-end node, such as base station and the terminal, one might wish to move the complexity to either transmitter or the receiver, depending on which one it is. So there is some flexibility there as well.
Thank you very much. I really appreciate it. I think you get me very curious about Faster-Than-Nyquist. I can give you that, and that's I very appreciate it. Thank you.
Any further comments and questions?
Yeah, I could ask questions. So hi.
Please,
Risto Vihma. So just messing up with the camera. Okay. So just this question. So thank you. Interesting thing and very interesting presentation. And my disclaimer is also I know nothing about this business. So, but then about this high order modulation, so 5G now has 256 QAM, which is difficult to implement. So, and then in specs requires some -30 decibel EVM. So then would there be benefit if you use this Faster-Than-Nyquist and low order modulation, 64 QAM, for example, or 128, or I would say, well, where would that benefit come from?
Yeah, perhaps I can start the answer here. Thank you, Professor Wichman, for the question. So yes, the answer is yes. So if we have, let's say, a high order QAM Nyquist signaling, then that operates at a certain spectral efficiency. Then another possible solution that we use a low order modulation and then accelerate the pulses to reach the same spectral efficiency. And on top of that, there will be gains in the signal to noise ratio. This is already reported in the literature. I don't recall the exact comparison, but for 256 and tau operating or accelerating the factor from a base Qpsk to reach the same spectral efficiency, I believe there was around 4 dB savings in the signal to noise ratio. Yeah.
Just to complement, I think interest is there in both low spectral efficiency regime as well as high. Actually, the fiber optic guys are, I guess, one of the communities deriving FTN, and their modulation orders are rather low in comparison to, the numbers we are talking about. Basically, it is, as Ebrahim said, for a target spectral efficiency of, say, 2, if faster than Nyquist. So rather than using plain Qpsk, using BPSK, but in a faster manner, or let us say, just back of the envelope calculation, Qpsk versus BPSK, but 100% acceleration at a target bit error rate. If the operational frequency in the latter is lower, then there is a SNR gain there. And then in higher order modulation, very high order levels, including our recent unpublished results, going up to 65K QAM. These are quite atypical levels, but they might be used in microwave links or in even coax cable for very short distances. So the promise is there in all those regimes, but as we are discussing, I think things have to be built beyond simulators, and it has to be seen whether this promise is really realizable or not.
Yeah, thank you. I think 4 decibels is indeed something, so that's worth pursuing. But then, as you said, so there are these challenges, and I could imagine so that synchronization might be one of them. So I'm used to watch eye diagrams, but I guess that wouldn't work in this case.
Yeah.
The good thing is that, the scenarios are so many. The operation of a sensor is very different than a supercomputer at a base station, so on and so forth. It is not clear to me, and that makes it exciting as a researcher. Really, where is the sweet spot when we take into account all the practical factors? Which construct is the right one, at least in the near future, for FTN to manifest its promise, if it can? It is still to be seen.
Yeah, thank you.
Any further comments or questions to Halim and Ebrahim? Then maybe I would like to have one if no one else has. So Halim, as you mentioned, you find this appropriate for the inclusion into the extended scope. I mentioned at the beginning that we are currently actually discussing how to extend the scope. And I would just like to add that already from the start, this ETI was scoped as dealing with research and promoting research in the community, both for self-interference cancellation techniques, especially applied to full duplex communications. Now, my question to you, are you aware of or did you think about how the existing, because the self-interference cancellation architectures, which we are using in bidirectional full duplex communications or even 3-node full duplex communications, have some specific architectural assumptions or algorithmical solutions. Of course, the literature is huge, but still the basic problem is the same, that the transmitter causes interference to the same receiver. And as Professor Smida mentioned, we are dealing here with 100 or higher 100 decibel suppression. So my question is, those type of algorithms or architectures, how would that be useful to help faster-than-Nyquist signaling, or what is how should I see the key relation between, how would it fit into that type of self-interference which we have been dealing with so far, mostly in the context with full duplex?
Yes. That connection or immediate extension is not there as far as I can see, to be honest with you. The dynamics of interference or self-interference is very different, as I very candidly mentioned at the end of my presentation. However, let me make remarks from two different angles. Now, if I look at as an FTN person or FTN fan, let me put it in that way. Clearly, this concept needs a push to go to the next level. Indeed, for instance, I am observing that METIS 2020 played a very important role to make a big jump, as well as Lund University's persistent activities over a decade. At the moment, although there is acceleration, big acceleration in the literature, but if an ETI like FT ETI, again, I'm not sure whether that is the right house or domain, but if it endorses, obviously there will be workshops and special issues and panels and all the activity. I think that will likely give a big boost. Now, from another angle, when FT ETI started, I'm not a member of the ETI, as you know, Gabor, but maybe several years ago, in the pre-5G era, pre-standardization era, this full duplex was a kind of magic. Many people in the community were skeptic whether it is doable. Canceling 120 dB interference doesn't seem to be reasonable, but that phase is, I guess, pretty much over. There is more confidence in full duplex. I'm seeing the interference here. Yes, so maybe it is, of course, your officers who will make the decision, but inclusion FTN might give further forward-looking viewpoint to this ETI, in which, from at least my perspective, my knowledge on full duplex is also limited. However, as an outsider, I can see that it is now a more established topic. If today it would be difficult to start a full duplex ETI if it were not there from 5 years ago. But including FTN may inject new blood to the area.
I see.
Going back to again your question, this is from signal processing techniques, I don't see FTN as just an immediate extension of full duplex.
I see, Halim. I very much appreciate this comment. And so basically, if I interpret your words correctly, you are suggesting that this could be a win-win situation, because on the one hand, we could give, or the ETI could give and the visibility and stimulating activities, as you say, to give this extra push, what FTN technology as such would benefit from. On the other hand, it would give us, or give the existing full duplex scoped ETI more forward-looking scope.
Yes, but keep in mind that my view is perhaps a bit subjective as an FTN fan. I am looking for a body to embrace this concept. So obviously the officers of this ETI, I'm sure, will make the right decision and judgment.
Thank you so much, Halim. We will indeed discuss this within the team. And I actually, Wendy also would like us to make some sort of a decision, and there's a process around the extension of the scope. So, but I will definitely keep you in the loop, and whoever is interested, please feel free to join our mailing list if you are not already on the mailing list, and reach out to any of us on the ETI list.
Thank you very much, Gabor, and everyone for the opportunity to present today.
Thank you, Halim and Ebrahim, for giving us this really stimulating, interesting talk. I'm asking again if there are any further other questions, comments. I take it as a no. Then thank you to all of you who attended the seminar today. Special thanks to the presenters, Halim and Ebrahim, and we keep in touch, and we inform each other about the progress of this. Thank you so much.
Thank you all. Bye.
Thank you.
Thanks.
Bye-bye.
Bye-bye.
Thank you. Bye.